But the whole idea here is that there's a compiler that bridges the gap between the world of data scientists and the world of embedded programmers. So in one of the keynotes this morning, it was mentioned that if we've got highly skilled, highly valuable people in the UK, providing them with the right tools helps them to be a lot more productive and competitive in a global environment. Good afternoon, everyone. So I'm James from ETAS, and to preempt the questions being typed in, what does ETAS stand for? It stands for Enhancing Tomorrow's Automotive Software. And one of the areas of software is AI, machine learning. And here, what are we talking about? Well, when we typically associate things with AI, we're talking about the blue boxing glove from the previous talk. So this is things like ChatGPT, it's big data centers, lots of power. Nobody's quite sure what the algorithms do. What I'm going to talk about is what if we can bring machine learning and AI to the kind of small embedded systems that we find in automotive ECUs, the little smart sensors, smart actuators that hang off on the fringes of a zonal architecture. So a couple of examples of what I'm talking about. So one tier one supplier we worked with, we're doing ultrasonic parking sensors, little ones that mount in your bumper. And their code base had grown over the years. It was all rule-based, and it had grown into this big mountain of spaghetti code, which was effectively unmaintainable. Nobody understood what it did. All the people who'd started writing it were retiring. So they had a project, and they replaced this code with a neural network, training it on all of the data that they'd collected over the years. And they found that was much faster, much easier to maintain, and crucially, it fitted into the ECU much better. And another point was, once they trained their model, they could take that model, qualify it, and then put it across a range of vehicles. So starting maybe with your typical four-door saloon, looking at an SUV, an estate, two-seater or whatever, just by using the same model, but changing the weights that model works with. So that gave them a much more scalable and efficient way to work with this system. Another example is replacing physical sensors with virtual sensors. So some of you might recognize the component here. I don't, but I'm told it's part of a motorcycle drivetrain. And the idea is to replace some of the force sensors in that by looking at the model of the behavior of the rotating parts of the mechanism. And of course, the goal here is saving costs. The more physical parts we can take out of the hardware, the cheaper the car becomes. And, a lot of people like that. But what are the challenges? Once you've built your AI model, how do you put that into an embedded world? Because in a lot of organizations, you find there's a split between the data world with people who understand how to build and train the models. And then there's the embedded world of the guys who are working with real-time operating systems and AUTOSAR or whatever. And there's very little overlap between them usually in terms of skills and experience, and even being in quite separate parts of the organization. So what we're looking for is a tool that bridges those two worlds and allows the benefits of machine learning to come down to typical embedded systems. Now, you might say, well, I've got a tool that creates models. It allows me to analyze my data, and it will generate nice ANSI C code from that model. And that's fine. If you want to test the model, verify that it works correctly, maybe use some of the techniques that the previous presenter was mentioning, that's fine. But once we want to take that code and put it in an existing ECU system, we need to think about some constraints. So first of all, we need a tool that's easy to use. It needs to be used by non-specialists. It needs to be easy to integrate into a tool chain. We don't want costly new hardware. Some of the chips we've heard described today are fantastic in terms of being multi-core and all singing, all dancing. But we're still thinking there's still a lot of simple microcontrollers in vehicles, and there's likely to be for quite some time. So we don't want to increase the hardware, we don't want to increase the power consumption too much, we don't want to increase the heat output, all of those kind of things. Typically, we want some functional safety support, so we want to know if code's going into a system, we want to be sure that it's actually doing what we expect it to do and be able to argue about that when somebody wants us to prove it. And then finally, it's an embedded system, so of course, the resource usage in terms of the computation time and the amount of memory that's available is always going to be limited. I've been in this game a long time. Nobody's ever come to me and said, hey, James, I've got plenty of spare memory here. Can you help me fill it up? So first time for everything, I guess, but hasn't happened yet. So I'm going to deep dive into just one area of this today, the resource efficiency, and cover some of the techniques that you can be aware of when looking at a tool that is basically compiling a machine learning model into embedded C code. So the first thing is that whatever model you're using, it's likely that there's going to be a lot of matrix and vector multiplication or dot products. So we've got a matrix of weights or parameters for the model, which need to be stored in memory. We're going to have a vector representing the input to the model and another vector representing the outputs from the model. And the sizes of them can vary enormously depending on the order of the model being used. And that means we've got to think about how much memory we're taking up. And we also need to think about the computation. There's going to be a lot of multiply and accumulation going on in this kind of system. So there's various variations of this basic theme for different types of neural networks. But the basic idea is you've got slices of input data, wherever they're coming from. You're multiplying them with some kind of filter, and that gives you an output value. So depending on exactly what kind of model you've got, there's variations, but the basic principle's the same. We need to think about the memory allocation, and we need to think about the efficiency of handling the calculations. Okay, so one of the things we can do, if we're talking about a compiler for machine learning models, well, a normal compiler is aware of the underlying hardware. So it should know a bit about the instruction set. So one of the things that's quite common when we're bringing data in to be processed, you want to check that the data's in range. So say you want to quantize the input into an 8-bit integer range. So a typical ANSI C library implementation will have a little function, and it says, right, let's look at the value, compare it to the upper and lower bounds, and saturate it as necessary. And that gives the assembler code in the big purple box there. So we've got, what, 1, 2, 3, 6 instructions there to do that operation. That's not bad. But say the compiler knows it's running on an ARM Cortex M7, and it knows, right, in the instruction set, there's a nice sign saturate instruction that can do the same job in one operation. So we've got a massive saving there. If you think of all the input values that need to be processed, that's a huge saving in runtime. So again, just like a normal compiler, we need to look at that kind of efficiency in the generated code. So the next thing is thinking about when we're loading in the data to perform our dot products. So as I say, typically we're loading in inputs, usually several values at a time. We've got some kind of filter mask with parameters that need to be multiplied against that, and that gives us the output value. And again, a naive way of doing that is you set these up in memory, you do your multiplication, and you get one output value. But again, if the compiler's any good, it should be able to say, well, I can use the instruction set again to interleave the registers, load more values than we actually need, because we're only going to, we're going to use some of this data multiple times. So only load it once, do multiple dot products in parallel, and get double the efficiency. So looking at benchmarks on this, you can reduce the memory loads by about 33%, which again is a huge runtime improvement. And you can really compress things down, but still get mathematically equal code. So you can still say the model that you trained on your desktop tool is going to behave exactly the same as the model that runs in the ECU. Another aspect is when you're doing these kinds of calculations is that if you've got this typical sort of 2D convolution where you're moving the filter mask over a matrix of inputs, once you've processed the first pixel with your mask, you're not processing that pixel again. So as you move through the matrix, the values become redundant. So you can reuse them for storing the outputs from the calculation. And this means that you can save about 50% of your working memory, which again is a huge advantage in a small embedded system. Okay, so having all of these optimization techniques and a compiler that understands how to use them is all well and good. But when we're trying to decide how are we going to implement our model in an embedded system, we're usually looking at some sort of trade-off between the runtime speed available and the amount of memory that's free in the system. So you want a compiler that's going to calculate this Pareto front. So it's searching through the space of all the possible models and then informing you and saying, right, here are the ones that touch upon the lowest bound in one of the dimensions. So if you're looking at a runtime critical application, which could be a braking system or some kind of torque vectoring motion control, you probably want the one that has the fastest runtime. But the trade-off for that is you're going to need more memory to support that. You get a different implementation, maybe some kind of predictive health monitoring, where you're storing values over a long drive. You think about a lorry driving up the M6. You're going to have several hours of operation storing values. So you want to make sure that those values don't mean that you run out of memory. So having this kind of Pareto front allows you to pick and choose which of the available models actually satisfies your requirements. And the nice thing is it's still guaranteeing that you've got the same numerical behavior between your PC training and the embedded runtime. Okay, so that's just a quick overview of the kind of techniques that are available. I'm sure it will surprise no one that if I say there's such a tool available on the market, and if you'd like more information, there's a URL there, or come and have a chat with me afterwards. But the whole idea here is that there's a compiler that bridges the gap between the world of data scientists and the world of embedded programmers. So in one of the keynotes this morning, it was mentioned that if we've got highly skilled, highly valuable people in the UK, providing them with the right tools helps them to be a lot more productive and competitive in a global environment. And the whole idea is saying, if people have got ideas how to use data, we can use it in existing ECU hardware without upgrading the cost. We can support functional safety. The tool will generate reports saying what optimizations it's made, how the code's been generated and why, and things like saying, okay, we can follow MISRA guidelines and that kind of thing. We can even generate tests to prove the numerical equivalence. We can get state-of-the-art resource efficiency. If you've worked with ETAS real-time operating systems, you'll know how small and fast they are. Every cycle is sacred. And lastly, this is proven at use. ETAS is part of the Bosch group of companies. So this tool's used across all of the different Bosch industrial divisions. So as well as being in your car, it could be in your kitchen in the appliances, it could be in your power tools, it could be in your material handling robots. So it's already out there and proven satisfactory for use across a major industrial organisation. Okay, so that wraps it up from me. So be happy to take any questions.
Thank you very much, Jim.